So hi everyone, my name's Lucy, and today I'll be talking about a piece of work currently being done by myself, Geraint Pratton and Patricia Schmidt at the University of Birmingham to build a Precessing higher mode surrogate waveform model which uses neural networks. So I'll provide some motivation behind this work first of all. The process of parameter estimation for a compact binary coalescence gravitational wave source, where we infer the source properties such as masses and spins, relies on us having accurate and efficient waveform models. To provide accurate and unbiased results, typically we want these waveform models to have built into them all of the physics that we might expect to see as part of the binary merger, which for a binary black hole can include things like precession and higher order modes. But there is a balance to be struck between completeness and building in all of the complicated physics versus speed of evaluation, because it's no use having the most wonderfully accurate waveform model in the world, but it takes years to do a real parameter estimation. So how do we ensure that the most accurate waveforms we can build will actually be usable within a parameter estimation process? So one way to do this is through the use of waveform surrogate models. A surrogate model is a reduced order model of an underlying slower model. It will typically be built over a predefined parameter space of masses and spins, and within that parameter space, it will produce waveforms which are really accurate to the ones produced by the underlying model, but with a much faster evaluation time. The first step to building a surrogate model is to define a reduced basis, because we assume that over our chosen parameter space, our training space, each waveform can be represented as a linear combination of time-dependent basis elements multiplied by some coefficients which depend on the intrinsic parameters. We use a greedy algorithm to build this reduced basis, which allows us to represent every waveform within our training space data in this way, to within some accuracy, which we call our greedy tolerance. So in the figure on the right, if the area of the plot, the white rectangle, is our entire training space, then building the reduced basis provides us with these red vertical lines. And now that we've compressed the problem to a smaller number of elements in parameter space, the next step is to build our empirical interpolant, which compresses the problem in time as well. So this process allows us to choose the most important time nodes shown by the blue horizontal lines on the figure. And by specifying any waveform at only those time nodes, the empirical interpolant will then be able to reinterpolate the full waveform to a high degree of accuracy. And the final step is to fit the basis coefficients at the empirical time nodes across our training space. And these points are represented where the places where the blue and red lines cross one another. And this fitting procedure can be done in a number of different ways, such as cubic splines, Gaussian process regression, or neural networks. And for examples of each of these techniques, as well as some more detailed information on building surrogate waveform models, I've included some more references down here. So in this work, we aim to build a proof of concept surrogate model for the Precessing higher order mode waveform model SUBNR V4PHN. This model is an effective one-body model, which solves the equations of motion of the binary to produce a waveform, and that makes it slow. This has also meant that it's difficult to use in parameter estimation without the use of additional tools to speed up likelihood evaluations, so a fast surrogate model may be a very useful thing. In order to build our surrogate model, we first need to split up the fully precessing waveform into components which are easier to model. So firstly, the waveform strain can be decomposed into spherical harmonic modes, and the modes we choose to include in our surrogate are listed here: the dominant quadrupolar 2-2 mode and 3 higher order modes. And next, we decompose each of these waveform modes into 2 parts: a coprecessing waveform mode, which is defined in a non-inertial frame, which moves with the precession of the binary, and also a rotation operator, which represents the rotation to this non-inertial coprecessing frame. When a fully precessing waveform is constructed in this way, this rotational transformation is often called twisting up. And additionally, the rotation operator can be defined in terms of 3 different Euler angles, and it's these which we choose to model with our neural networks. And as for the coprecessing waveform modes, we split each of these 4 modes into an amplitude and a phase and model each of those 2 things separately. So in total, we have 3 Euler angles and 4 modes, each split into an amplitude and phase, which makes a total of 11 different components to individually model in order to get the fully precessing signal. So next we need to define our training space over which we wish to build our surrogate. And because this is a proof of concept, we choose a very limited mass ratio range between 1 and 2. We also restrict our waveforms to be single spin, but the primary spin can be precessing and have magnitude up to 0.8. We generate a total of 200,000 waveforms in this way across our training space. Each waveform is 10,000 m long, which corresponds to a total mass binary of 44 solar masses being generated from 20 Hertz. And we also generate a 10,000 waveform validation set in exactly the same way. This will be used as a check during the neural network training, and also a 10,000 waveform test set, which will be used to compute mismatches once our training is finished. So in the table on the right-hand side, you can see for each of the co-processing waveform mode components, the details of how we built our reduced bases. We generally use an absolute greedy tolerance of 10 to the minus 6, but we do adjust these in a couple of places in order to increase accuracy or to reduce basis size to a manageable amount. So onto the models. In the schematic diagram, you can see the neural network architecture for the co-processing amplitudes and phases. Our input layer is 4 neurons, one for each of our 4 intrinsic parameters, the mass ratio and the 3 primary spin components. And then we have 4 fully connected hidden layers, each with 320 neurons, leading to an output layer, which is the same size as the reduced basis and also the number of empirical time nodes for that component. So in order to produce the full waveform component, we need to input the intrinsic parameters into the neural network, reinterpolate the output from the output layer, and then do any inverse scaling that we need in order to produce the fully predicted amplitude or phase. So some results. In the left plot, you can see the co-processing mode amplitudes, and on the right, the co-processing mode phases, both the true EOB data in the dashed dark gray lines and the neural network predictions with the solid colored lines for each of the 4 modes we modeled for this particular binary, the parameters of which are at the bottom. So in the context of our parameter range, this is a moderate mass ratio, moderately processing binary, and you can see from the plots that the agreement is extremely good between the real data and our neural network predictions. This plot on the left shows mismatches across our unseen 10,000 waveform test set between the true SCOBNR V4PHM co-processing modes data and the co-processing modes predicted by our neural networks for each of the 4 modes we modeled. The mismatch is defined by the equations on the right-hand side, and this metric is often used by waveform model developers as a measure of how well 2 waveforms agree. So a mismatch of 0 indicates complete agreement, whereas a mismatch of 1 indicates that the 2 waveforms are completely orthogonal. And our waveforms, again, are generated from 20 Hertz for a 44 solar mass binary, and we use white noise in these match calculations. So we can see that the bulk of all of our mismatches for every single mode is below 10 to the minus 2. And for the 2-2 mode, it's actually significantly better than this. We note that there are tails in our odd M modes, the 2-1 and the 3-3 mode, but these occur in parameter space where there is very little binary asymmetry, so near to equal mass with very little precession. And these 2 modes will be heavily suppressed in those regimes and won't contribute much to the overall processing strain signal anyway. So we haven't talked that much about the Euler angles thus far, but on this slide, you can see for the same binary I showed a couple of slides ago, the true Euler angle data in dashed red and the neural network prediction in solid blue. And again, we see excellent agreement for this binary, just as we did for the co-processing modes. So lastly, I'm going to talk about the model speed. We expect each of our neural networks to evaluate in a time of about 1 millisecond on a CPU to generate a single waveform component. That's 1 amplitude, phase, or Euler angle. And therefore, our total evaluation time will be about 10 milliseconds plus the cost of twisting up the waveform. So this represents a significant speed up compared to the underlying model of about 100 times faster. It's also a factor of roughly 5 times faster compared to the recently developed surrogate model, which I've referenced here. And additionally, since our neural networks are built using TensorFlow, they can be evaluated on GPUs for an additional speed up factor of up to 10 times. And since GPUs are highly parallelized, it's possible to produce large batches of waveforms using our surrogate simultaneously when it's executed on a GPU. So in conclusion, this work centered around building a proof of concept processing higher order mode surrogate waveform model of SCOB NR-V4PHM using neural networks. We have so far successfully modeled the co-processing frame waveform modes with a bulk accuracy of less than inaccuracy of less than 1%, even for higher order modes. And the final step will be to combine these modeled co-processing modes with the modeled Euler angles to twist up the waveform and model the fully processing signal. Because of the neural network implementation of our surrogate, we expect a significant speed up compared to the original SEOBNR V4PHM model at roughly 100 times faster on a CPU, with further speed up when evaluated on a GPU. Thank you so much for listening, and I welcome any questions.
Thanks very much, Lucy. And that was almost perfectly within the second to time. So congratulations. One question which I had was, so you cover how long it takes to actually produce a waveform from the trained model, but how long does the training take? I mean, if you decided to use a new approximate or, NR or something to generate it, how many months does that set you back?
The actual training of the neural networks can be done within roughly, at the moment, it's taking about 6 or 7 hours on a GPU. The thing that takes a long amount of time is actually producing your training data. So if you wanted to build a similar thing on a slightly different parameter space, you would need to go and generate a whole bunch of EOB waveforms. And that at the moment is the thing that's taking on the order of days or weeks. So yeah.
Okay, yeah, thanks. Well, I don't see any other questions just at the moment, but again, if anybody does have any, I'm sure Lucy will be able to answer them on the Slack channel as we go on. Otherwise, thanks very much, Lucy. And our next speaker